Electrons are used in radiation therapy for superficial treatments. There are two components to this. Number one is electrons have a high skin dose compared to photons, as well as the electrons have a physical range within tissue, so at some point the electrons stop depositing their dose completely, as opposed to photons, which will keep going through the patient indefinitely. So if I have two patient surfaces here, one with a photon field and one with an electron field, my photon field will continue to have isodose lines at depth, whereas the electron field will stop. The only dose component at depth for the electron field is something called photon contamination or Bremsstrahlung contamination. So electron treatments are primarily used for superficial treatments, usually skin tumors, a lot of times breast boosts for boosting the lumpectomy cavity. Dosimetric characteristics of the electron field. So if I draw a percent depth dose curve for let's say 6E, so 6 MeV electrons, my surface dose is right around 75%. I get a fast buildup. My Dmax is right around 1.5, similar to 6 MV or 6X. And then I get a very fast fall off. Contrast this, so I'm just going to call this 6E, which is the same thing as 6 MeV electrons. Contrast this to 6X, where I get a surface dose between 30 and 40%. I get a buildup region. It peaks at Dmax, and then I get a fall off. So contrast these at depth, the doses. Parts to the electron curve. Things with the electron curve you need to know about are going to be surface dose. Okay. How does surface dose change with energy? For photons, surface dose decreases with increasing energy. For electrons, surface dose increases with increasing energy. You need to know about something called D90, D80, Dmax, R50, and R sub P. Okay, so D90 is going to be the depth at 90% isodose line, which roughly you take the energy divided by 4. Okay, that gives you a good approximation. D80 is going to be the 80% depth of the 80% isodose line. Again, roughly is E divided by 3. Kahn specifies these more accurately. Your physicist should also have these written in a data book somewhere. Dmax in general increases with increasing electron energy, but we find out, when you actually look at percent depth dose curves with the electrons, that the higher energies don't really exhibit one particular Dmax value, but rather a plateau. R50 is going to be depth of the 50% isodose line, and this is normally an energy qualifier, so it's how the physicist specifies the effective energy of the electron beam. R sub P is going to be the practical, we'll call the practical range of the electrons, and the definition for this, or the approximation for this, is energy divided by 2. Okay, so I would encourage you to build the following table out and verify it at your clinical sites as well. So we'll have electron energy, and 6, 9, 12, 15, and 18. Electron energies depend on manufacturer as well as what the site orders up. Usually, sites will have some range in here. They might have like a 20 or a 22E. Maybe you have a 16 instead of a 15. It's up to you to verify your own electron energies on your machine. What I want you to do is build the following table: is build surface dose, D90, D80, Dmax, and R sub P for each of these, and convert it to memory for your particular site. I always stress dosimetrists at your clinical sites or at your job that you will eventually get. You need to kind of commit these to memory, or a general rule of thumb. You need to remember them. Okay. So how does percent depth dose, I'm sorry, let me go back. Percent depth dose. Let's draw it a little bit bigger. And let's compare two different energies. Okay, we'll compare 6E sorry if the scales aren't going to be drawn out correctly. So this is going to be 6E, and then we'll compare that with 20E. And I'm only picking these two because they are drastically different. So points to make about the two percent depth dose curves and how percent depth dose, or how the percent depth dose curves are changed by changing the electron energy. First thing, skin dose. Skin dose goes up with increasing energy. They roughly work in, let's see, 5% increments. So 75% at 6E, 80% at 9E, 85% at 12E, 90% at 15 or 16E, and then 95% at your 18, 20, or 22E. Okay, but again, those are just rules of thumb. You need to go back and verify that with your data book. Next thing is going to be D80 and D90. I guess here we have D max for 6E. And notice that for 20E, there's no specific D max. You get this broad plateau, you know, of 100%. So D max is usually, can either be specified, you know, in the middle, or sometimes the physicists will write a range. You know, it'll go from 1.5 to 2.5. Okay. Next is D90. So D90, and then you'll have D80, you have R50, right, and then you have R sub P. R sub P is found by taking the tangent to your fall-off line. If you track it and extrapolate it down to the axis, this is where R sub P is at. On the 6E, I would track the tangent down to the axis, and R sub P would be here. R sub P for 6E is going to be 6 divided by 2. Energy divided by 2 is going to be roughly 3 centimeters. R sub P for 20E is going to be 20 divided by 2, or 10 centimeters. R sub P represents the practical range, or the physical range of the electrons travel in the tissue. So anything after this point is purely bremsstrahlung contamination. Bremsstrahlung contamination comes from the electron interactions within the treatment head and the scattering foil, and it is X-ray contamination. They're photons that are contaminating the beam. They're always present, except they're dwarfed by the dose of the electrons back here, and then they show up after the electrons stop depositing their dose, and you're left over with the contamination. It's roughly 0.5% for 6E, and it can vary between 3 to 5% for 20E. Okay. Again, R50 is used as an energy qualifier by the physicist. The dosimetrist, as a treatment planner, you're really not going to have to worry about it too much. It's just another beam qualifier. So, prescribing with electrons, typically, again, all situations are different, but typically prescriptions with electrons are prescribed at the 90% isodose line. And there's a reason for this. The reason is that we usually only do one electron field. So if I have a patient surface here, field is coming down, my isodose lines look like the following. This is going to look similar to talking about normalization the other time. And my tumor sits in here. This is my 100% line. These are my 90% lines. Remember, I have a build-up and fall-off 90% line. So here and here. This is my 100. Okay, 100% goes right through the target. I can't just treat half the target. I have to normalize. You can do one of two things. You can either calculate to a lower depth, which you normally don't do with electrons, or what you can do is you prescribe to a lower isodose line, namely the 90% isodose line. And then we encompass the entire target. The same thing would be if I drew a target here on my percent depth dose curve. I can't cover it with 100%. I need to renormalize and make 90% my new 100%. therefore encompassing the entire target in the isodose. Okay. Let's see, inverse square law. There's inverse square law for electrons. I guess we'll have to go over that in a different point in time because that'll take a little explanation. Anyway, so you got it. Look this over in Con, Bentel, electrons. Memorize this, and definitely memorize this for your board exams because you will need it 100%.